Welcome to our deep dive into the fascinating world of organic chemistry mechanisms. In this video, we'll unravel the step-by-step processes that drive organic reactions, helping you understand not just what happens, but why it happens. Whether you're a student or a curious learner, mastering mechanisms is key to predicting outcomes and solving problems in organic chemistry. Let's start by exploring what a reaction mechanism actually is and why it's so important in understanding the behavior of organic molecules. Get ready to see chemistry in a whole new light as we break down complex ideas into simple, logical steps. Reaction mechanism is like a detailed map showing the journey from reactants to products. It explains each transformation, highlighting the movement of electrons, the breaking and forming of bonds, and the intermediates that appear along the way. Understanding mechanisms allows chemists to predict new reactions and design better experiments. In organic chemistry, mechanisms are often illustrated with curved arrows, which show how electrons flow during each step. By following these arrows, you can visualize the invisible changes happening at the molecular level. Let's look at how these arrows work and why they're so useful. Curved arrow notation is the language of organic mechanisms. Each arrow starts at an electron source like a lone pair or a bond and points to where those electrons are going. This simple visual tool helps us keep track of electron movement, which is the heart of all organic reactions. By mastering curved arrow notation, you'll be able to interpret and construct mechanisms with confidence. We'll practice using these arrows in real examples so you can see how they bring clarity to even the most complex reactions. Organic chemistry features a variety of reaction types, each with its own characteristic mechanism. The main categories include substitution, addition, elimination, and rearrangement reactions. Each type involves different patterns of bond breaking and forming, and understanding these patterns is crucial for predicting reaction outcomes. In the next scenes, we'll explore each type in detail, starting with substitution reactions and see how their mechanisms differ. Substitution reactions are among the most common in organic chemistry. In these reactions, one atom or group in a molecule is replaced by another. There are two main types, nucleophilic substitution and electrophilic substitution. Each follows a distinct mechanism, but both involve the exchange of groups attached to a central atom. Let's start by looking at nucleophilic substitution, which is especially important in the chemistry of halides and alcohol. SN1 mechanism stands for substitution nucleophilic unimolecular. It typically occurs in two steps. First, the leaving group departs, forming a carbocation intermediate. Then the nucleophile attacks the carbocation, resulting in the final product. SN1 reactions are common with tertiary alkyl halides, where the carbocation is stabilized by surrounding groups. The rate of reaction depends only on the concentration of the substrate, not the nucleophile. This mechanism often leads to a mix of products due to the planar nature of the carbocation intermediate. SN2 mechanism, or substitution nucleophilic bimolecular, is a one-step process. Here the nucleophile attacks the substrate from the opposite side of the leaving group, pushing it out in a single concerted action. This leads to inversion of configuration at the reaction center, a hallmark of SN2 reactions. SN2 is favored by primary substrates and strong nucleophiles. The rate depends on both the substrate and the nucleophile concentration. Let's see how this mechanism works in practice and why it's so important in synthesis. Electrophilic substitution is especially important in aromatic chemistry. In this mechanism, an electrophile replaces a hydrogen atom on an aromatic ring. The reaction proceeds through the formation of a reactive intermediate, often a carbocation, which then loses a proton to restore aromaticity. Common examples include nitration and halogenation of benzene. Understanding this mechanism helps explain the reactivity and selectivity of aromatic compounds in organic synthesis. Addition reactions are central to the chemistry of alkenes and alkanes. In these reactions, two atoms or groups add across a double or triple bond, converting unsaturated molecules into saturated ones. The mechanism varies depending on the reactants, but the key feature is the breaking of a pi bond and the formation of two new sigma bonds. Let's look at some common addition mechanisms, starting with electrophilic addition. Electrophilic addition is a classic mechanism for alkenes. The reaction begins when an electrophile attacks the electron-rich double bond, forming a carbocation intermediate. The nucleophile then quickly adds to the carbocation, completing the addition. This mechanism explains the regioselectivity seen in reactions like hydrohalogenation, where the more substituted carbocation is favored. Understanding this process is key to predicting the products of alkene reaction. Nucleophilic addition is common in carbonyl chemistry, such as reactions involving aldehydes and ketones. Here, a nucleophile attacks the electrophilic carbon of the carbonyl group, breaking the double bond and forming a new single bond. This mechanism is fundamental to many important reactions, including the formation of alcohols and the addition of Grignard reagents. Let's see how nucleophilic addition works and why it's so versatile. Elimination reactions are the reverse of addition reactions. In these processes, two atoms or groups are removed from a molecule, often resulting in the formation of a double or triple bond. The most common types are E1 and E2 eliminations. These mechanisms are crucial for creating alkenes and alkanes from saturated precursors. Let's explore how elimination reactions work and what factors influence their pathway. The E1 elimination mechanism involves two steps, much like the SN1 substitution. First, the leaving group departs, creating a carbocation intermediate. Next, a base removes a proton from a neighboring carbon, resulting in the formation of a double bond. E1 reactions are favored by tertiary substrates and weak bases. The rate depends only on the concentration of the substrate. This mechanism often competes with SN1 in similar condition. E2 elimination mechanism is a single-step process. Here, a strong base removes a proton while the leaving group departs simultaneously, resulting in the direct formation of a double bond. E2 reactions are favored by strong bases in primary or secondary substrates. The reaction rate depends on both the substrate and the base. E2 is known for its stereospecificity, often requiring an antiparaplanar arrangement of the leaving group and the proton. Rearrangement reactions involve the migration of atoms or groups within a molecule, leading to new structural arrangement. These mechanisms often occur during carbocation intermediates, where a more stable carbocation can be formed by shifting a hydrogen or alkyl group. Rearrangement is common in reactions like the Wagner-Meerwein and Pinnacle rearrangements. Understanding these processes helps explain unexpected products in organic synthesis. Radical reactions are another important class of organic mechanisms. These involve species with unpaired electrons called radicals. Radical mechanisms typically proceed through initiation, propagation, and termination steps. Common examples include halogenation of alkanes and polymerization reactions. Radicals are highly reactive and can lead to chain reactions, making them both powerful and sometimes difficult to control. Initiation step in a radical reaction involves the generation of the first radicals, usually by breaking a bond with heat or light. For example, in the chlorination of methane, chlorine molecules absorb energy and split into two chlorine radicals. This step is crucial because it sets the chain reaction in motion. Without initiation, the reaction cannot proceed, highlighting the importance of energy input in radical chemistry. During the propagation step, radicals react with stable molecules to create new radicals, continuing the chain reaction. For instance, a chlorine radical can abstract a hydrogen atom from methane, forming hydrochloric acid and a methyl radical. The methyl radical then reacts with another chlorine molecule, producing chloromethane and another chlorine radical. This cycle repeats, allowing the reaction to proceed rapidly once started. Termination step occurs when two radicals combine, removing reactive species and ending the chain reaction. For example, two chlorine radicals can recombine to form chlorine gas, or a chlorine radical and a methyl radical can form chloromethane. Termination steps are less common than propagation, but they are essential for bringing the reaction to a close and preventing runaway reactions. Pericyclic reactions are a unique class of organic mechanisms that occur in a single, concerted step without intermediates. These reactions involve the redistribution of electrons in a cyclic transition state. Examples include the Diels-Alder reaction and electrocyclic reactions. Pericyclic mechanisms are governed by orbital symmetry rules, making them predictable and highly useful in synthesis. Diels-Alder reaction is a classic example of a pericyclic reaction. It involves the combination of a diene and a dienophile to form a six-membered ring. This reaction is widely used in the synthesis of complex organic molecules because it forms multiple bonds in a single step. The mechanism is concerted, meaning all bond changes occur simultaneously, and the reaction is highly stereospecific. Electrocyclic reactions involve the opening or closing of a ring through the movement of electrons in a conjugated system. These reactions are also concerted and follow specific rules based on the number of electrons involved. Electrocyclic mechanisms are important in the synthesis of cyclic compounds and are often triggered by heat or light. Sigmatropic rearrangements are another type of pericyclic reaction. In these mechanisms, a sigma bond migrates across a conjugated pi system, resulting in a new sigma bond and a shifted structure. The most famous example is the Cope rearrangement. These reactions are highly predictable and play a key role in the synthesis of complex natural products. Organic mechanisms can be classified as concerted or stepwise. In concerted mechanisms, all bond changes occur simultaneously in a single step, as seen in pericyclic reaction. In stepwise mechanisms, the reaction proceeds through distinct intermediates like carbocations or radicals. Understanding the difference helps chemists predict reaction rates, stereochemistry, and possible side products. Intermediates are short-lived species that appear in stepwise mechanisms. Common intermediates include carbocations, carbanions, and radicals. These species are often highly reactive and determine the pathway and outcome of a reaction. By identifying intermediates, chemists can better understand and control organic reactions, leading to more efficient syntheses. Every step in a reaction mechanism passes through a transition state, which is a high-energy, unstable arrangement of atoms. Transition states represent the point of maximum energy along the reaction path. Although they can't be isolated, understanding transition states helps explain reaction rates and activation energies. Visualizing these states is key to mastering organic mechanisms. Activation energy is the minimum energy required to reach the transition state and start a reaction. Factors like temperature, catalysts, and the nature of reactants influence activation energy. Lowering the activation energy speeds up the reaction, which is why catalysts are so important in both laboratory and industrial chemistry. Catalysts are substances that speed up reactions without being consumed. They work by providing an alternative pathway with a lower activation energy. In organic chemistry, catalysts can be acids, bases, metals, or even enzymes. Understanding how catalysts influence mechanisms is crucial for designing efficient and selective reactions. Choice of solvent can dramatically affect the mechanism and outcome of an organic reaction. Polar solvents can stabilize charged intermediates, while nonpolar solvents favor radical mechanisms. Solvents also influence reaction rates and selectivity. By understanding solvent effects, chemists can optimize conditions for desired reactions. Stereochemistry refers to the spatial arrangement of atoms and molecules. Many mechanisms like SN2 and E2 have specific stereochemical outcomes. Understanding how mechanisms affect stereochemistry is essential for synthesizing molecules with the desired three-dimensional structure, which is especially important in pharmaceuticals and natural products. Regioselectivity describes the preference for forming one structural isomer over another in a chemical reaction. Mechanisms often dictate which position on a molecule will react, as seen in Markovnikov and Anti-Markovnikov additions. Understanding regioselectivity helps chemists predict and control the products of organic reactions. Chemoselectivity refers to the preferential reaction of one functional group in the presence of others. Mechanisms help explain why certain groups react while others remain untouched. This selectivity is crucial in complex molecule synthesis where multiple reactive sites may be present. Some reactions can produce more than one product depending on conditions. Kinetic control favors the product formed fastest, while thermodynamic control favors the most stable product. Mechanisms help explain which pathway is followed and how to influence the outcome by changing temperature or reaction time. Energy diagrams are visual tools that show the energy changes during a reaction. They illustrate the relative energies of reactants, intermediates, transition states, and products. By analyzing energy diagrams, chemists can understand why certain mechanisms are favored and how catalysts or solvents affect the reaction pathway. Reaction coordinate is a concept used to describe the progress of a reaction from reactants to products. It's often represented on energy diagrams, showing the path taken through transition states and intermediates. Understanding the reaction coordinate helps visualize the mechanism and identify rate-determining steps. The rate-determining step is the slowest step in a reaction mechanism, setting the pace for the entire process. Identifying this step is crucial for understanding how to speed up or control a reaction. Mechanisms often reveal which step is rate-determining by comparing the energies of transition states. Mechanisms are often proposed based on experimental evidence such as kinetic studies, isotope labeling, and product analysis. These experiments help confirm or refute proposed pathways, making mechanisms study a dynamic and evolving field. By analyzing data, chemists refine their understanding and improve reaction design. Isotope labeling involves replacing an atom in a molecule with its isotope, allowing chemists to track its movement during a reaction. This technique provides direct evidence for the steps in a mechanism, helping to distinguish between competing pathways. Isotope labeling has been instrumental in elucidating many classic organic mechanisms. Kinetic studies measure how fast reactions occur under different conditions. By analyzing reaction rates, chemists can infer which steps are involved and how they depend on reactant concentrations. Kinetic data is essential for distinguishing between mechanisms like SN1 and SN2, which have different rate laws. Computational chemistry uses computer models to simulate reaction mechanisms and predict outcomes. These tools can visualize transition states, calculate activation energies, and suggest possible intermediates. Computational studies complement experimental work, providing deeper insight into complex mechanisms. Learning mechanisms can be challenging. Common pitfalls include misplacing arrows, overlooking intermediates, or confusing similar reaction types. Practice and careful analysis are key to mastering mechanisms. Remember, every arrow and step must make chemical sense, and checking your work helps avoid mistakes. To master organic mechanisms, focus on understanding electron flow, practice drawing curved arrows, and study real examples. Work through problems step by step and don't hesitate to revisit challenging concepts. Over time, you'll develop intuition for predicting mechanisms and outcomes. Mechanisms aren't just academic, they're vital in real-world chemistry. From drug development to materials science, understanding mechanisms enables chemists to design new molecules and processes. The principles you learn here are the foundation for innovation in countless fields. Let's recap what we've covered. Organic mechanisms explain how and why reactions occur using curved arrows to track electron flow. We explored substitution, addition, elimination, rearrangement, and radical mechanisms, as well as the roles of intermediates, transition states, and catalysts. Mastering these ideas is essential for success in organic chemistry. Now that you have a solid foundation in organic mechanisms, you're ready to tackle more advanced topics and real-world problems. Keep practicing, stay curious, and remember that every reaction tells a story. With these skills, you'll be well equipped to explore the endless possibilities of organic chemistry.